So for the third exercise, the idea is to actually download a little bit of data and make some charts. So we want to be able to not just look at all the different data and make visualizations that are just online, but we want to be able to download a little bit of data and look at some time series of rainfall and make some simple charts. So go from only doing things online to actually recovering some data and using it on our own computers or within our Google Colab, as it may be. So just like before, we're going to import the same modules, and we can test that this works. And I'm defining again my Kathmandu point. So I have my Kathmandu geometry with my x and y coordinates, and I see that this is working. The data that I want to use today is the same one that we looked at this morning, which is this CHIRPS daily precipitation. So this daily rainfall data from 1981 to 2026 at a resolution of about 5 kilometers. So this is a quite dense data set that we can use, but it's not so massive that we are going to have trouble processing it. We can check again the size of our data, 16,500, which means we want to subset to only using a smaller amount. In this case, for this exercise, I'm going to use 3 years of data. When we did it this morning, we just did the average of 1 year of data and made a map. Now what I want to do is I want to make some charts, and it's nice to see 2 or 3 years of data and see was this a more rainy year or a less rainy year between a certain time period. So I'm setting my rainfall data as my CHIRPS collection, and I'm filtering to just the last couple of years. So 2023 until 2026. And if I check the size of this, I see that I have 1,100 days of data. So that's enough that it will be interesting to look at some charts, but not so much that it is hard for us to download. So the way that we need to download this data is a little bit funny. You can't just say, here's my point, sample all of this data and give it to me as a nice clean chart. We have to do a few steps in between. And those are always a little bit funny because Earth Engine has its own formats and these kind of things. So what we're going to do in the next few pieces is how can we go from this not so pretty Earth Engine code to something that is easy for us to save into an Excel file, for example. So I've defined a little function here, just like we've been using all morning to do the apply scale factors and things like this. This one is going to create a time series out of a set of images. Or it's going to create a time series from one specific image. First, it's going to check the date. So this is how Earth Engine stores the date, system time start. So that's the Earth Engine internal date format. And to get the value at that date, we use, again, a reducer. But in this case, we use reduce region. So reduce region allows us to apply any function, an average, a sum, whatever you want to do, over a specific region. So that could be a square, that could be a whole watershed, it could be a whole continent, or it could be, in our case, one single point. I'm setting my geometry as KTM. So that's this point that we defined up here, which is just one XY coordinate. So this is going to get rainfall data only over this specific point. And if you want to try this on somewhere that you have your own weather station, feel free to switch this point. All you have to do a different location is change this geometry. Now I'm saying that what I want to do is I want to get the mean. It doesn't really matter in this case since we're only getting one individual point location. The mean, the sum, the max, all of these things will be the same. But if we were doing this over a wider area like a watershed, you have to decide, do you want the rainfall sum or the rainfall average, these kinds of things. We're interested only in the precipitation variable, so we just check for precipitation. And then we have to do this sort of funny formatting where I make a feature that has a date, which is my date of my image, and I'm making sure I format it as year, month, day, so when I read it again into Python, I know what that date actually is. So it's not just a whole bunch of numbers. And then we have a rainfall field, and that's where I'm going to store this value that I get out of my reducer. So this is going to get me the date and the value of rainfall for one specific day, one specific image. To apply this to 3 years of data or 5 years of data, we use a map. Map is a function that's also in Earth Engine and in many programming languages, and basically it says, apply my function everywhere. Here's my function, apply it to each image, and give me back the result. So it's similar to a reduce, which is applying something like an average over all pixels at once, but it's instead applying something specific to each time point. So for each image in my rainfall, so each day of rainfall, I want to map this function, which will turn the image into one value and one date. Which means when I do this get info and try to download the data, it's only going to give me back this little dictionary or this time series thing, and it should go quite quick. What it gives me is this fun and long list of values. It would be nice if it just gave me a date and a rainfall, right? But Earth Engine is always formatting these things in these web JSON and these dictionaries that make sense for when computers are accessing the data and they have these structured data sets, right? So if we want to turn this into something useful for us, we have to go through each one of these features and say we only want these properties, we want to know the date, and we want to know the rainfall. The rest of this information is not useful for us, right? We can't turn this directly into a plot. And for that, we want to use, oh, we got to scroll, there we go. We want to use a for loop. Now, we talked about this a little bit yesterday during our short Python introduction, right? That we can loop through a list and, for example, apply some value or print something. I put a link in here that has a more detailed explanation of these for loops and the ways you can use them. But the short and sweet version of it is that we want to go through our time series features. So that's exactly this time series thing that we made here, wherever it is here. This, which contains this really long list of things that we want to reformat. And for each one, we want to look in the features, get the properties of the features, get the date out of the properties, and get the rain out of the properties. And this should then give me a long list of dates and values. And we can see that some dates there's no rain, and some dates there is rain. Now we're getting to something that looks a little bit more reasonable, right? Now we have this long list of values, and we just have to store them somewhere so we can make a chart. So we can use the exact same for loop, except now we're creating two empty lists. So these square brackets mean a Python list, one for the dates and one for the rainfall values. And I've added these two extra lines at the end of my for loop, one that appends my date time to the list and one that appends my rainfall value to the list. So when I run this, I should now get something. I should get these. Can I add one here? If I look at dates, for example, I should now have a long list of these Python dates, and it's in a format where Python knows that it's time and it knows when things are, right? Now if I look at my rainfalls, it should just give me a long list of values for rainfall at that date, which means we can make a plot. This is using my matplotlib library, the PLT library, which is for making figures. I make a figure of a certain size, 10 by 5 centimeters, and then I plot on the x value the dates, and on the y value the rainfalls. And I set my y minimum to 0. We don't have negative rainfall. And I put a label on my x-axis of date and a label on my y-axis of daily precipitation. And now we can see that for our specific spot in Kathmandu, we have pulled out 3 years of daily rainfall totals. And it's now in this format that it's on our computer. We can save it to an Excel file. We can make different charts. We can do some sort of analysis on it. We can do whatever we want with this data. It's no longer on Google Earth Engine. We've gotten only the small specific data that we wanted for this location, for this data set. And now we can work with much, much smaller data than trying to download this whole giant precipitation data set. We can, for example, get the maximum. So I'm going to use my numerical Python, NumPy library, to turn my rainfalls into an array, so something that NumPy knows how to work with. It can get their maximum value. And I can also check when that maximum value occurs. Which day was the highest rainfall total? And I can print those values and also put a vertical line on my plot at this maximum rainfall date. And this should then give me the same plot showing that the biggest rainfall total that we had in Kathmandu was sometime in September of 2024. That must have been a very, very wet day if it was the top out of 3 years of monsoons. So I tried to compare this to the Kathmandu rainfall weather station from DHM, but that data is no longer online. You can access the countrywide forecast, but you can't get the specific weather data. So I can't tell you if this is exactly what DHM measured as the most rainy day. If it's a little bit different, it's because this rainfall data that we're working with, the satellite data, is over a 5-kilometer grid. So it's the average rainfall rate over a sort of bigger area. So it won't always be the same as if you have a rainfall station or some sort of meteorological station that's measuring one single point. So the satellite data is nice because we have it everywhere, but it's not as finely resolved as the station data. So sometimes, in some contexts, it's better to have one or the other, or combine them together and see if you can calibrate one with the other. So we aren't limited to only rainfall data, right? We've looked at all sorts of different data sets today, and we can use this exact same time series analysis function to get out different data. So we can plot, for example, snow cover, temperature, vegetation, rainfall, all of these things for the same point using a few short commands. So I pulled out a point here in Langtang, and I'm defining my Langtang point as this XY coordinate. You can see that the Google Maps is reversed. You have to switch them around. And I can see that my point that I chose here is at about 3,500 meters, so a much higher elevation location. I want to add on top of my chirps rainfall, I'm also interested in temperature data, so surface temperature data from MODIS. This is this mod 11 temperature data, my daytime surface temperature, and for all of these data sets, I'm filtering to just 2 years. I'm also getting this NDVI data, so I ignore that link here. This is this NDVI, all from MODIS. If we look at this MODIS temperature data, we can see that we have this 1 kilometer data, 1,000 meters pixels, and it's daily global land surface temperature. And we have a daytime temperature and a nighttime temperature. The one that I'm loading in here is the daytime temperature. So I can take these 3 data sets, 2 years each of data, and I can create 3 time series. This is the exact same create time series that we used before to get our rainfall data. I'm now just using it for rainfall with the precipitation variable, which I'm naming rainfall, with my temperature data set, so all my Landsat or my MODIS temperature data, which is the LST day 1 kilometer variable, which I'm just renaming to something simple like temperature. And then my vegetation, I'm getting NDVI and calling it vegetation cover. Now, this next block, I just took this for loop. This is dates and datas, for loop, append the data. This is exactly what we just did above, except I'm making it into a little bit of a function so that we don't have to keep running this for loop. We can just say, okay, I want to do it for my rain series. I'm interested in rainfall. I want to do it for my temperature series. I'm interested in temperature, and so on. So if we run both of these blocks, we should now get 3 sets of data. Maybe we can look at one of these. If I look at, let's call temp. See what that looks like. So temperature should now be this long array of values. Obviously, they are not in the in degrees centigrade, right? We need to apply some scale factor to convert them to actually be in degrees centigrade. But we have some values over Langtang for Langtang for this set of years, which means that we can then quickly plot all 3 of them. So we can plot rainfall on the top, daily temperature in the middle, and daily vegetation cover on the bottom. So this is just using my rain dates and my rain values, my temperature dates and my temperature values. See, I've scaled my temperature to be degrees Celsius, and my vegetation dates I've scaled to be vegetation greenness. And so we can compare all these different kinds of data sets with just a few lines of code. We can reuse the same functions that we used for our first analysis for rainfall for some other kind of data set. And we can plot these different things on top of each other or next to each other and use them for comparisons. Now, maybe we're actually going to get this. So I'm going to do one more test here with a much higher resolution precipitation data. This is GPM precipitation, which is half hourly data. So every 30 minutes, there's GPM precipitation data from 1998 until yesterday. So this one's updated quite frequently. I think it's only one day of latency, which is nice. It's at about a 10-kilometer resolution, so it's not quite as high resolution as the daily chirps data, but we do have half-hourly data. That means that for a 2-month period, for example, 2 months from May to July, we have almost 3,000 values. So way, way more data density. We can use the same functions. They just might take a little bit longer, though apparently not. That went really fast. And we can now have this half-hourly precipitation that only covers a couple of months. I think Google Colab has like a straight shot to the Google servers. You can download things much faster. This half-hourly rainfall rate is maybe interesting on its own, but it's quite sparse, right? You have these sharp peaks when it rained and then nothing. So if we want to compare it to something like a daily rainfall total, we can go back to this pandas library. This is this library that Bodo was working with yesterday for the GNSS data, which is good for working with kinds of tabular data. So Excel data, CSVs, spreadsheets, this kind of thing. And what we want to do is we want to turn this into a pandas series. So when we use the pandas library to say, okay, these are my values, and use this index of my dates. This is exactly the data we just took from Earth Engine. Now, pandas knows how dates are related to each other. It knows that within a 24-hour period, that's all one day. Pandas has some internal knowledge of how these dates work, which means that we can use some pandas functions, for example, resample, which will take all of the data from one day and apply some function. For example, here, a sum. We want to sum our precipitation to a daily total. Since it's half-hourly data, I'm dividing it by 2. Otherwise, you're going to have too much precipitation. We can also do a maximum, minimum, all sorts of different things you might want to do on this data. Now that it's in a pandas time series, there's access to a whole lot of different time series analysis functions, ones that you might not have available on Earth Engine. So this can then make us maybe a nicer chart that's showing these raw half-hourly precipitation values overlaid with a daily precipitation sum and the single daily max rainfall rate. So when is that max happening in the day, which should match up with these highest black points, which are my rainfall rates. All right, I think there's some further information also in here if you want to get more into these data sets, and there's also a whole community organization of these kinds of data sets. If you want to download the data, you can also do this very simply with pandas if you want to save it for future use. This is exactly what Bodo was showing yesterday as well. So you can go from sampling this big data from Earth Engine and then saving it to your computer for making whatever kind of charts or analysis you want to use. And with that, I think